The Camber lens blank improves on the spherical lens blank by offering a continuously increasing base curve to better match the different powers in each zone of the finished progressive lens. The state-of-the-art digitally designed back surface of the lens is calculated in mutual accord with the unique Camber variable base curve. Notice this back surface is not a finished progressive design. The back surface design is further enhanced, when desired, by a complete set of individualization parameters. The digital design, combined with the individualization parameters, are processed together on the back surface of the lens. Notice the lens is still not a final progressive in design. The combination of curves on both sides of the lens creates the finished Camber progressive lens. An advanced digital lens that accommodates an expanded prescription range, offers better cosmetics, and yields user-preferred near-vision performance.
Freeform lens technology has revolutionized our industry, allowing us to create increasingly advanced and customized lenses. What makes freeform lenses better than conventional ones?
The visual quality of a lens decreases as we move away from the optical center due to oblique aberration, which arises when light rays enter the lens at an angle. The light rays refract in the lens, preventing them from focusing on the fovea and generating power errors.
The wearer perceives a blurring in the peripheral area, which increases as we move away from the center of the lens, leaving a reduced area of clear vision. IoT's digital ray path lens calculation technology significantly reduces peripheral blur. For this purpose, it considers the wearer's parameters and the position of the lens in the calculation of each design. Ray tracing simulates oblique aberrations for each gaze direction and associated focal distance by modifying the back surface of the lens to give the wearer the best vision at every angle. In this way, we achieve a significant reduction in the effects of oblique aberration. The improvement is obtained with advanced geometry, but it cannot eliminate peripheral blur for wearers by itself. The new version of the digital ray path technology gives us the answer to overcoming any geometrical limitation. IoT includes, for the first time in the ophthalmic industry, a key aspect in the calculation and minimization of oblique aberrations, the wearer's accommodation.
Accommodation is the natural mechanism that allows us to focus accurately at different distances. Up until now, custom lenses were only optimized to view objects at a single associated distance. However, by stimulating and relaxing a small part of their accommodation, the wearer can focus sharply over a range of distances at the same point on the lens without moving their eyes or changing their gaze direction. This range of distances is known as accommodative object space.
Digital ray path can now simulate oblique aberrations in the accommodative object space, considering all focusing distances and gaze directions, thereby achieving a more accurate and realistic optimization according to how wearers will use their lenses. In addition to the inclusion of the accommodative object space, it uses an innovative mathematical model that intelligently minimizes oblique aberrations, considering the wearer's accommodative power. To understand this, it is necessary to know the components of the error induced by oblique aberration and how the visual system perceives them.
This induced error is composed of a cylindrical power error, which generates distortion, and a spherical power error, which produces blur. The visual system reacts differently to both errors. The eye has no mechanism to reduce the cylindrical error and perceives it as distortion. The use of a small fraction of accommodation can cancel out the entire negative spherical error component.
Digital ray path can now maximize the reduction in cylindrical power error and keep the residual sphere component, which is the one that can be easily compensated with accommodation. The result is a fully customized lens with a more efficient compensation of oblique aberrations that offers the wearer impeccable visual quality and precise, comfortable focusing. IoT, see the difference.
IoT's Steady Plus methodology is an improvement of steady methodology that is only available on Camber Steady Plus progressive lens designs. Steady Plus methodology carefully balances the mean power required for intermediate and near vision, achieving a perfectly symmetrical and smooth distribution. Steady Plus methodology has proven results in double-blind studies. Steady Plus methodology is only available from IoT.